Okay, we are going to begin trying to generalize Green's theorem, in other words, the fundamental theorem of calculus in 2D to 3D. And to do this, we're going to need to define geometric objects. So stuff that makes sense even in 3D. And so we're going to reformulate Green's theorem using these objects. These objects will be called the divergence and the curl. And so let's see how these objects will come in. So let me just state Green's theorem for you again. So if you have a closed integral of essentially work along a curve, then it's equal to this integral with this funny looking integrand, qx minus py, where our force is pq. It's that vector field. And what we're going to do is we're going to replace this qx minus py with something more geometric. And the way we're going to do this is, first off, I want to see what happens if we remove the minus sign. Right? I mean, it's kind of strange looking. So, and notice that, and also q, which is the y part, it's with the x. And p, which is the x part, it's with the y. So it's kind of asymmetric. So what happens if we make it more symmetric? So in other words, if we put q with the y and p with the x. So what I'm going to do is I'm going to do the following replacement. I'm going to replace p with minus q, so I'm going to switch the x with the y, and similarly I'm going to replace q with p. Remember, I want that minus sign gone, which is why I'm only using a single minus sign. So let's do that switch and see what we get. So we get a q y with a plus sign, and we get a px with the same sign. Now let's do that on the left-hand side. So first of all, this is just px plus, I'm sorry, if you take f dot dr, the left-hand side is px dx, I'm sorry again, p dx plus q dy. So now if we do the swap, we're going to have minus q dx plus p dy. I'm going to put that back into a dot product. So this is pq, again, we want the f to be the same, but now the d is going to change. The d is going to change to a dy minus dx. Remember, this used to be just pq dotted dx dy. So now it's dy minus dx. So what I've done now is I've created this identity. pq dotted dy minus dx is actually equal to px plus qy. So this is actually more symmetrical, don't you think? So what's the significance? What's the geometric significance? I promised you some geometry. So dy minus dx, let me draw our curve really quickly here. So dy will make, let's see, we'll make this our dy. dy dx. I'm exaggerating the drawing here just to make it more clear. But now if I change this around, then this large dx goes to the y component. So again, just to try to make it clear, I'll draw it like this. So now we have minus dx and dy. So that's our new vector. And I'm going to draw, and I'm going to put that vector right here. So it's at the same point. So notice how this is a tangent vector. That's what we started with, dr. And now this is a normal vector. Okay, so actually, if dr was the unit tangent vector times the arc length, then in fact, this new thing, dy minus dx, it's just the unit normal vector times ds. Right? Okay, so this is actually just n times ds. Whereas before, it was the tangent vector times ds. Okay? And now this thing we're going to call, as promised, I'm going to call this the divergence of our vector field. So, we have finally gotten this identity. F dot the normal times the arc length is equal to the divergence of F times the area. So I'll just call this the second Green's theorem. It's really equivalent. And the point is that the only real difference is a minus sign, and this is reflected in changing the tangent to a normal and in changing that expression here with the minus sign to this divergence. But the geometrical meaning changes, and let's talk about what these things represent. So first of all, let me just rewrite the identities here. First of all, we have f dot dr, which we're going to call it tangent ds. This is, of course, just qx minus py. And then our second, just by switching the minus sign, we have f dot n, the normal part instead of the tangent part. And this is now equal to px plus qy. And this I will call the divergence. And this thing I'm going to call the curl. As you'll see why. So, let me sort of draw what these things represent. Let's start with the divergence. So, what is px plus qy? Well, it's if our curve is small, then it's approximately it's 1 over dA times this line integral. And this, of course, is just a sum over f dot n. So the normal projections. So let's draw it out. So if our vector field points here, it'll be projected along the normal direction. If our vector field points in this direction, it'll be projected along the normal, and so on. So really, what this represents is, if you think of f as a velocity field, then this sum of these projections, it equals the flow out of our region. Of whatever particle it represents. And so if px plus qy is positive, there's an inflow. If it's negative, there's an outflow. Okay? And if it's 0, there is no flow. And so in the 0 case, let me just draw that in red. We actually have rotation of the vector field, and the particles do not escape the surface. Okay, so in other words, the divergence, it represents the local flow rate of our vector field. And you can also think of it as accumulation rate. Because if there's an inflow, then that means we're accumulating particles. If there's an outflow, that means we're losing particles. And actually in electricity and magnetism, the electric field, the divergence of the electric field is actually equal to the charge. And this is known as Gauss's law, which you don't need to know, but I'm trying to give some context for why this divergence expression is useful. So let's turn to the curl now that we have an intuition for why the divergence has a geometric meaning. So for the curl, I'm going to draw this curve. Okay. So we're actually projecting against the tangent directions now. And let me just recall what the Green's theorem says, that the projections along the tangent directions, they're equal to this curl. So nearby at the point, the curl, it's simply, it looks like these line integrals. So if we understand what the line integrals look like, then we can get an intuition for the curl. So remember that work is just F dot dr. So really, the curl is the local work done by the vector field along small closed curves. Okay, and there's another interpretation of this, and you can also think of it as the local rotation rate, right? Because if f is tangent, then we have this situation. Again, where there are no particles escaping, and so really what's going on is the particles are rotating within the surface, and there's no inflow or an outflow. So we can say how much it rotates about the z-axis. Remember, there's always a z-axis in 2D. Okay, and finally, we remember that the curl is just this silly qx minus py expression, and so this expresses how non-conservative it is. So if it's 0, then f is a gradient, right? It's a gradient vector field, and in this case, it's actually there's a name in the mathematical literature called irrotational, and this comes from this local rotation rate thing. If it has no curl, it does not rotate. In fact, it'll in the irrotational case, it'll often be normal. Not always, but it'll often. And so all of these ideas, they'll extend to 3D. And because again, we have gradients in 3D, so we know what non-conservative means. We also have work in 3D, so that works just fine. And in divergence, we also have, you can define inflow and outflow of particles within a surface. So, and of course you have charge in 3D, so it all makes sense. So this is the benefit we get from introducing these additional tools. So I won't talk about the 3D formulation immediately because we need a couple more ideas. First, we need what is the divergence and the curl in 3D anyway. How do we do it? And the second thing we need to do integration. Because we need a 3D dA, and we also need to know what this normal vector is doing in 3D. So once we have these, we'll be able to do Green's theorem in 3D. Okay, thanks for watching.